Okay, I've put my mug up here on the corner, and I got to remember to look at the green dot. I've gotten out of practice with that since I put my physics sport completely online. I once again I apologize that we're having to finish the course this way, even though this is kind of thank goodness we live in this time now where we can do these types of quick fixes and things like that. Oh yes, my lunch. I'm gonna eat my apple here in a minute while we're going through this now. The next thing is kind of herky jerky because but it'll be okay. Um, the OpenStax book does not follow our slides. I'm used to teaching from our slides, and I've kind of molded some of the OpenStax books together. Here's the big idea of what we're going to do. We're going to look at electromagnetic waves. We're not going to mess with the energy of the waves or anything like that, which might be important, but I'm not sure if it's on the MCAT or anything. So not a big deal. One of the big things, before I go any further, one of the big things I wanted to make sure that we got done this summer was that while you're studying for the MCAT in a year or so, or whenever you're going to be doing that, that you have the ability from doing this course, that you then have the ability to go ahead and read the physics, or when you're going through the MCAT book or something, to be able to go, oh, okay, I at least know enough physics that I can at least put this together, even though we never did this in class. Okay, that I think that would be very helpful. We're going to do electromagnetic waves, which includes polarization, which is really kind of cool. And so that jumps to chapter 27 in OpenStax, but it stays in chapter 24 for the electromagnetic waves. And then we're going to look at light acting like a particle. In other words, we're going to look at reflections and refractions, refractions, and then we're going to really kind of hit lenses. Lenses is a big deal. I heard on the MCAT for optics type stuff, and that'll be the 3 days. So the 24 and 27 today, the end of 27, chapter 25 from the cut now, and a little bit of 25 and 26 mixed up with the OpenStax. Okay, but the slides will be coherent and they will follow the lectures. All right, so I'm going to butt out and just go ahead and get started here with this part. Okay, so let's go to let's just go and play this from the current slide so you get a big picture of it. Here's James Clerk Maxwell. Good Presbyterian. I had to throw that in. Scotsman. Genius, mathematical genius and physicist. And he's the one who predicted the intersection between waves and how light waves caused by electromagnetic waves. Okay. And his predictions: electric field lines originate on a positive charge and terminate on negative charges. These are from Maxwell's equations. Okay, these are the 4 big ideas. Oh, these are all things we've done. As the permanent is related to the constant, is related to the constant of that permittivity of free space, so that it can act in a vacuum. And magnetic field lines are continuous, having no beginning and no or end. No magnetic monopoles are known to exist, and the strength of the magnetic force is related to. That's an interesting thing, that the magnetic fields are continuous and they have no beginning or no end, where charges do. They'll terminate. A charge will start on a electric field, start on a proton and end on an electron. A changing magnetic field induces an electric motive force. That's what we just had the test over. And the direction of the EMF opposes the change. The third is Faraday's law of induction and includes Lenz's law. So let's just look and see what these equations look like. All right. Here's Lenz's law, done mathematically. Makes your head hurt. And these are over closed surface. See, these are integrals taken over closed surface. This is the differential form. This is the integral form. All right. So that's 3-dimensional calculus there, and that's for physics 460. Not even your 250 fellow 250 students. They don't do that. Okay. So anyway, and here's what an electric field looks like, an electromagnetic field, long straight wire. Okay, this is the electric field. Boom, 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 boom. You get a long straight wire going up and down, bang, 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 and then it moves. Okay, then the electron stays here, but what happens is it propagates a wave. So this is what is known as a transverse wave, unlike a wave on the ocean, which is a longitudinal wave. Okay, and so we just have this electromagnetic wave. Now, this thing induces, believe it or not, a magnetic wave. Well, we've learned that, okay? And here's our magnetic wave that's spinning around it. When it's really, really close, what did we learn? We've got a current going up, okay? We've got a current going up, and when the current is going by convention, when the current's going up, we've got a B field twisting around this way. And then when this electric field starts to propagates further away from the wire, it stays perpendicular at all times, stays perpendicular, so it's going to be going in and out like this, when the electric field is going to be going up and down like this. All right? All kind of cool stuff. And how fast do they go? C. Okay? They go the speed of C. All right. And then you might, I might allow you to bring this slide in. It depends on, for our next exam, which shows you the electromagnetic spectrum. Notice, FM rate 10 to the 8. Now this is the frequency and this is the wavelength because they're going the speed of light. So I'm going to stop here. This was the introduction, and we're going to stop here, and I'm going to make this one short little movie. Okay? Out of here. So let me hit this.